Welcome to another video. So in this video, we're going to talk about the reciprocal identities to some trig functions. We'll see how to use them and be pretty brief. We'll talk about what happens when a trig function can be assumed to be on a unit circle and when it can't, and maybe you can think of it both ways. So we'll talk about how to deal with them and find other trig functions given that we know just a couple of them, or one and the quadrant in which it resides. So let's get started. We've seen this a couple times, but I want to make sure that we're really comfortable with how these functions interplay. So if we define sine of theta as y and cosine of theta as x, relating to a unit circle, and sine of theta gives you that y coordinate of a point on the unit circle, and cosine theta gives you the x coordinate. And tangent of theta is the comparison of those two, the y over the x. Well, remember something though. This is for a unit circle. What that means is that the radius is 1. So this would really be y over 1 and x over 1. We're going to talk about that in just a little bit and how you can consider this, this particular trig function to relate to a unit circle or to relate to something that's bigger than unit circle where your radius is more than 1. Or less than 1 even. So then we also talked about cosecant, secant, and cotangent, and that those are called reciprocal functions of these trig functions. So when we have sine of theta equals y, well, if that's y over 1, cosecant of theta is 1 over y. But wait a minute. If cosecant theta is 1 over y, and y is sine theta, then we can also think of this as 1 over sine theta. And the same thing works for secant theta and cotangent theta relating to their respective trig functions. So we can see cosine of theta is x. Well, that's x over 1. Secant theta, therefore, is 1 over x, or secant theta is 1 over cosine, because x is cosine theta on that unit circle. Tangent of theta is y over x, so cotangent is x over y, but because y is sine theta and x is cosine theta, we can also think of tangent as this relationship of sine over cosine for whatever angle you have, and cotangent as cosine over sine. The big deal here really isn't to memorize these like verbatim as far as formulas, but to get the idea. You can tell that I'm really trying to repeat myself on cosecant matches up with sine, and secant with cosine, cotangent with tangent. That's an easy one because it has the same name. But people oftentimes get these two things confused. Why? I think because that starts with a C and this starts with an S. So they want to pair them up. That's not the way that it works. So I'm really trying to get you to remember that cosecant and sine are reciprocals of one another. Secant and cosine are reciprocals of one another. Tangent and cotangent are reciprocals of one another, which means that, yes, these formulas are nice, but honestly, it's just take your fraction and reciprocate it, and you will find secant for sine, secant for cosine, cosecant for sine, cotangent for tangent. And they go back and forth. That's really the drive behind this. So we're going to practice this very quickly just to show you that this is not all that bad. So let's look at this angle. And sine of this angle is 4/5, and cosine of this particular angle theta is -3/5. And they're asking you to find the rest of those 4 basic trig functions. You go, okay, is it that hard to do? Not really. Work your way through with the reciprocal identities. Now, we're going to talk a lot about this. Firstly, why do they give you 2 of them? Why is there sine of 4/5 and cosine theta of -3/5? Do you even need to know the angle, first off, to determine these other trig functions, and why are there 2 of them? Let's answer the second question first. Why do they give you 2 trig functions? The reason is because with those 2 trig functions like sine of theta and cosine theta, we can determine where this angle actually is, in what quadrant it is. And that helps us find out the other trig functions and the signs of those trig functions, which is very important to do, especially with tangent, because that's not given. So here's a couple things we should know. This should be in your head right now. We should understand that if sine is positive, so is cosecant. That's why I'm having you make that relationship between them, because they'll always have the same sign. If cosine's negative, secant's negative. Again, those pair up. Those are reciprocals of one another, so they have to have the same sign. Taking a reciprocal does not change your sign. Now, tangent and cotangent, we really wouldn't be able to say, if we covered that up and didn't know it, we wouldn't be able to say what the sign of tangent would be. Why not? Well, because if you look at sine of theta, it comes into our second question, but if you look at sine of theta has 4 over 5. Now, you can think of this 2 different ways. This is answering the second part of this question. Is this on a unit circle or not? It doesn't even matter. Well, you could think of this as a y of 4 and a radius of 5, in which case it would not be on the unit circle. You go, okay, well that's possible. We're going to deal with that in just a little bit in the second part of this video. Or you could think of this as, well, wait a minute, 4/5 is 0.8. Remember that the range of sine goes from -1 to 1, and every value between there. Do you remember that? Sine theta is from -1 all the way to 1. All these y values, all those blue values. So somewhere in there, you're going to hit 0.8. Now watch very carefully. 0.8, here's, let's say y equals 0.8. There are going to be two outputs for sine theta that give you positive 4/5, 0.8. And we could consider it to be on a unit circle. It'd be like having a y of 0.8 and a radius of 1. That would be here or here, let's say, somewhere in there. But wait a minute. Cosine and all the other trig functions, it would matter what quadrant we reside in so that we would know the sign. So putting this all together, I'm going to kind of repeat a little bit of what I said. Number one, why are you given 2? So that you can determine the signs of the rest of your trig functions. It's very important. So we know that sine is positive and cosine is negative, or sine theta is positive, cosine theta is negative for this particular angle. That's going to help us here. So that's great. Second part of this question, so it tells you the quadrant, and we'll talk about that in just a second. The second part of this question is that on a unit circle? Does it even matter? It doesn't really matter for 2 reasons. I'm going to say them again. If you consider this to be on the unit circle, this would be like 4/5 over 1. You'd have a y of 4/5 and a radius of 1. That'd be y over 1, or 4.8 over 1, if you will. That would be on a unit circle. Now, why in the world are they the same? That's another question that we should ask. Why are they the same? Why doesn't it matter? It has to do with similar triangles. So imagine something. Imagine a y of 0.8, that's 4/5, and a radius of 1. Now grow it, make it a y of 4 and a radius of 5. Nothing changes due to the fact that those particular angles, sine of that particular angle, has to do with a ratio, a comparison of 2 sides. Y over the radius, in this case, would be 1, or you consider 4 over 5. If you multiply 0.8 over 1 times 5 over 5, you're going to get the same relationship, 4 over 5. That angle does not change as our triangles get bigger and bigger and bigger. It's going to be the same exact relationship. So, long story short, it doesn't really matter. What does matter is determining the quadrant, that's why we're giving 2 of these things, and making sure we understand the reciprocal identities. So let's determine the quadrant here. If sine is positive, and we don't have that, this is go back to the first question, if we don't have that thing, there's no way to determine the rest. If we had no idea that cosine was negative, remember sine on a unit circle would be, sine of theta would be 0.8, that's positive 0.8 here, or 0.8 here. That's 2 different points on this unit circle. We needed to be 1 point to find out the rest of our trig functions. So we'd say, all right, if sine is 0.8, remember sine is positive here. We're either here or here. If cosine is negative, we can't be in the first quadrant, but only in the second. And that locates the quadrant for us. So let's take a moment to review this for a second. Do you remember that in quadrant 1, all of our trig functions are positive? So sine, cosine, tangent, and the reciprocal functions, they're all positive here. In quadrant 2, only sine is positive, and therefore cosecant is positive, but cosine is negative. Here, only tangent is positive, and cotangent is positive. That's why I'm making those connections for you. In quadrant 4, only cosine is positive, and therefore secant is also positive. So if we wanted to find a quadrant where sine is positive, that's 1 or 2. But cosine is negative, well, remember, you're either in 1 or 2, and now cosine is negative says you have to be here. That's what this means. It says sine is positive, cosine is negative. That's locating the quadrant for you, and that will help you determine the signs, specifically in this case, of tangent. So let's walk our way through it. I've talked a lot about it. Hopefully you understood the point that, can you consider this on a unit circle? Yes. Yes, if you think about this as 4/5 over 1, then that's 0.8. That's on the range, -1 to 1. There will be a point on this unit circle with a y value of 0.8 somewhere. And this is the angle that's giving you that y value. That's exactly what's happening. It can happen in 2 locations, either here or here. That's why we need this to say, it ain't this one, it's got to be that one. and that puts us in quadrant 2. So is it on a unit circle? Doesn't really matter, but you can consider it to be here. If not, then it's just a bigger circle, and you have a radius of 5, and that's fine too. The point is that we can determine the quadrant given 2 trig functions or knowing a quadrant that just gives it to you, but we have to know that for the signs of the rest of it. So let's see. If we know that sine and cosecant have this relationship of being reciprocals, then sine of theta is 4/5 means that cosecant theta is 5/4. And that's what I want you to remember, is that sine and cosecant are reciprocals of one another. We shouldn't have to go back to like a formula sheet every time for reciprocal identities. How about cosine theta? If cosine theta is negative 3/5, then secant theta is the reciprocal. Reciprocal functions do not change signs, so this is negative 5/3. Now tangent. This, in this particular example, is why we needed to understand that that was negative. You see, if we went back here and said, oh, hey, yeah, let's imagine that our 4/5 sine of theta equals 4/5 or 0.8 or somewhere in the unit circle is right there. If we imagine that, well, then tangent would be positive. If we imagine this one, then tangent would be negative. How do we know which one? This was the whole problem. This is why for sine of 4/5, and you got, hey, your y value here is 4/5 or 0.8. Either somewhere over here, remember 0.8 is about here, somewhere over here, somewhere over here, somewhere in there. Well, it matters for tangent. So we had to know that cosine was negative to say it's not this y value of 0.8, it's this y value of 0.8. So go up the y until 0.8, you're going to hit 2. You're going to have 2 outputs there. It's this one that we want, because it said cosine is negative and therefore quadrant 2. What that means is that tangent has to be negative. Well, we're going to see that bear out, because when we take a comparison of positive divided by negative, you're going to get a negative. So it does work for you, but without this one, you'd have no way to tell. You could not do this if you did not understand that that cosine was also negative somehow. I hope that makes sense to you. So tangent theta says, all right, let's go ahead and take sine over cosine. We know that's y over x. Sine theta is y. That is your y value, 0.8. This is your x, negative 0.6. We're just comparing them. We're just dividing them. So sine divided by cosine. If we multiply by the reciprocal there, so 4/5 times 5/3, we get negative 4/3 if we maintain that sign. The way that I always do this is I always figure out, if I have to find all the trig functions, I find tangent first, and I don't redo cotangent. I understand that cotangent is the reciprocal of tangent. I don't need to go back to my formulas if I understand the relationship amongst my trig functions. So with reciprocal identities, I think that, hey, tangent theta is negative 4/3, cotangent theta has to be negative 3/4. That's how we can find all of these trig functions given just a couple of them, or given one of them, and then a quadrant to determine the signs of the rest. Now, I'm going to preface what we're going to do after this next example, which you should do on your own. What I'm going to do is I'm going to tell you, well, what if we only know one trig function and a quadrant? Could you find out some more of this stuff? Yes, but it requires knowledge of what the formula of a circle is, and using it's really a Pythagorean identity. Using that to find a missing side, really, of this triangle on a unit circle. So we'll do that in just a bit. At this point, I would hope that you could figure out what these trig functions are. The first thing I want us to do is really look at this and think: sine theta is positive, cosine theta is positive. Think about the quadrant there. What quadrant do you have to be in if both sine and cosine are positive? Not that one, sine's negative. Not that one, they're both negative. Not that one, cosine's negative. This one, both of them are positive. And so we understand that if sine's positive, cosine's positive, that angle that we don't even know lies somewhere in this quadrant. We're in quadrant 1. What's that tell us? Well, that tells us that tangent is also going to be positive. All of our trig functions should therefore be positive. Remember that cosecant has the same sign as sine. Secant, same sign as cosine. Tangent and cotangent also have to have the same sign because reciprocals do not change signs. I hope you're sticking with me. So let's think about cosecant theta. Because these are reciprocals, I know that cosecant theta, for whatever angle we have here, is going to be the reciprocal 2 over square root of 3. Which, when you rationalize the denominator, multiply by square root of 3 over square root of 3, that's 2 square root of 3 over 3. Now, secant theta. Secant theta is the reciprocal of cosine. So for whatever angle that is, we're going to have 2 over 1. Tangent. Tangent takes sine, or y, and divides by cosine, or x, for whatever angle you have. So that's square root of 3 over 2 over 1/2. If we understand that we're going to multiply by the reciprocal, we're going to get the square root of 3. Now, because we figured that out for tangent, it's just a matter of reciprocating for cotangent. So that's 1 over the square root of 3. Or again, if you do rationalize that, that's square root of 3 over square root of 3. So 1 times square root of 3 is square root of 3. Square root of 3 times square root of 3 is 1. So that's just, 3. So square root of 3 over 3. And we have all of our trig functions. So the last thing that I wanted to talk about here is kind of prefacing where we're going to go next when we talk about inverse functions. So this one you couldn't really do it very easily, but I want you to check this one out. Could you find the angle if sine of square root of 3 over 2, sine of theta is square root of 3 over 2 and cosine theta is 1/2. Could you find the angle that gives you that point? You go, what do you mean the point? Well, the point is cosine theta gives you an x coordinate. That is an x coordinate. Sine of theta gives you a y coordinate. That is a y coordinate. And now maybe you'll see that you need both of them to determine a unique point on this unit circle. That's how inverses work, is a unique point here. So let's see about that. If our x is 1/2, let's look at this unit circle. If our x is 1/2, that puts us here, or it puts us here. Notice something. I could not figure out what quadrant this is in unless I had another trig function or knew it already. Or we defined it specifically so that we're bound between a couple quadrants. Now that's what we're going to do with inverses just a bit. But for right now, you can't do the rest of this because you'd have 2 points that you could pull from. You could pull from an x of 1/2 here or an x of 1/2 here. And your signs, these signs, positive, negative signs that I'm talking about, would change for sine, cosine, tangent, and cotangent, and all these other things. So the issue is I need another trig function to determine that. So let's see. If cosine theta is 1/2, that puts us here or here. There's not another positive 1/2. Obviously, that's the case because 1/2 is right here on the x-axis. So we're either an x of 1/2 or 1/2. Sine being positive square root of 3 over 2 says, oh yes, this is the one point you're talking about. That's a unique point. That says that the angle that would give you that is 60 degrees, or pi over 3. So we're going to start doing that when we get to a lot more videos. Honestly, we're going to start thinking about that. Like thinking, what would this have to be? What angle would cause this to happen on a unit circle? So let me do a little recap before we go on. Can you consider these to be on a unit circle? Yes, if this is less than 1, which it has to be. That's the range of sine and cosine. So you can think of this as some sort of a decimal or fraction on a unit circle. Now, it doesn't really match up very well with an angle, does it? Because 0.8 is not on here as like 60 degrees or something. So we can think of this as a unit circle. Do you have to? No, you don't. You can think of this as a similar triangle that you've made bigger. And by doing so, you still have the same ratio. 4/5 over 1 is the same as 4 over 5. What's that mean? The y of 0.8 compared to a radius of 1 is the same exact triangle, just made bigger, if you have a y of 4 and a radius of 5. That's why this stuff is so nice. And we can change between a unit circle and a right triangle later on. I hope that you remember that when we get there. The other thing is you need to know 2 trig functions, or at least know 1 trig function and a quadrant. to figure out the signs, positive or negative, for the rest of your trig functions. Let's move on. I'm going to show you the case where we can think about this as not being on a unit circle so that we can find more information. Hang on. All right, let's keep on rolling. So I have another example on the board, but before we talk about it, and as we talk about it, I really want to make sure that I'm clear about what is going on and why we consider this to be either on a unit circle or not, and get the same exact result. We're talking about similar triangles and the way that angles are congruent as we make them larger or smaller in similar proportion, which means equal proportion. So let's take a look at it. Now, if you remember, we talked about this one time and I made the reference to a right triangle and I said, hey, we can think of sine of theta as just y. What? On a unit circle, why? Because the radius would be 1. And if the radius is 1, we'd get y over 1 and cosine over 1 and y over x. That's not different for tangent. But what if we enlarged that triangle and said, okay, let's make this a little bit bigger? Well, can we consider sine, cosine different a little bit? Yeah, we can consider that to be the relationship between the opposite side, the y side, and the hypotenuse, whatever r is. And that's something that we can deal with. So here's what that means. If you have sine theta equals some sort of a fraction, some ratio, you can consider this to be one of two things. Either you can consider that to be a complete y value somewhere on the unit circle if it's between -1 and 1, which it has to be, or you can consider this to be two sides of a right triangle that can be inscribed on some sort of a circle. Now, what do I mean by that? Well, this is the equation of the circle. Now, it should look a lot like the Pythagorean theorem for you, and it is. It's the same thing, because you can inscribe a right triangle onto that unit circle, or any circle with a radius of whatever the r is. And so we're going to talk about that. We're going to say that, hey, if you can identify your r, so let's say for sine, your y and your r. If you had a y value and you had an r value right there, could you find an x value? Yes. Would you have to find an x value to complete all the trig functions? Yeah, you would, because notice cosine and tangent, and therefore secant and cotangent, they need an x value. And so if you have sine, there's no way to figure out cosine and tangent without doing a little bit of extra work. I'm going to show you exactly how that works and why we're able to do it. So let's take a moment for a second. So we understand that sine of theta is this relationship of y. Y over 1 for a radius of 1, or y over r for a radius that's not r. Does it even matter? It doesn't matter. I'm going to show you that. So let's say that y is 12. Why am I getting that? Well, I know that sine theta is y over r. Okay, r would be 13 here. Now, what if you don't like that? What if you think, well, wait a minute. I know that sine of theta is a y value, right? So these are all y values. So can I make this 12 over 13 with a radius of 1? Yes, you can. 12/13 is somewhere between -1 and 1. 12/13 will be some y value, really close to here, that is noticed as positive, right? Positive y is going to hit your unit circle in two places here with a radius of 1. Yes, you can consider sine of theta to be a y value with a radius here with a radius of 1. Now let's look at the triangle and see why it doesn't really matter how we consider it. So if our y value is 12/13, and our r is 1, this is not drawn to scale, but I want you to notice something. Let's say that I multiply both of all the sides of my right triangle by, here's 12/13, here's 1. So this is 1 from here to here, and that vertical is 12/13 on a right triangle. First question, could you use Pythagorean theorem to figure out this missing side? Here's x squared plus y squared would equal r squared, or x squared plus 12/13 squared equals 1 squared. Now you might be thinking, using that fraction is not going to be very nice in a Pythagorean theorem. And you're right. That's why I'm giving you a different way here. So check it out. Now let's say for a second that if this y value, this y is 12/13, and this radius or this hypotenuse is 1, well, we know about similar triangles, or we should, that I can take all of my sides and multiply them by some number. It's called scalar multiple, but some number, and grow all those sides in the same proportion. And in doing so, I'll get a similar shape. Now, what's that mean? Well, similar shapes maintain their angles. So the angles on similar shapes, corresponding angles, are congruent. That means equal. So let's see about this. If I multiply all of these sides by 13, why 13? Because it gets rid of my fraction. Let's multiply it. Then 12/13 times 13 would just be 12. And that side would grow to 12 if I multiplied everything by 13. 1 times 13 would be 13. Obviously not to scale. And whatever this x is, I'd multiply it and get x times 13, whatever that would be. Now take a look at it. Did the angle change when I went from the small triangle to the big triangle? No, it didn't. So if the angle didn't change, sine of that angle can't change, which means that we can put this in a different relationship, or at least consider it differently. Something on the unit circle, remember you could draw a circle here and that would have a radius of 1. Great, sine would be considered as 12/13 over 1. Or not on a unit circle, radius of 13. Sine of that angle would be 12 divided by 13, y over r. This height over the radius. Either way, do you see it? Do you see the same thing? 12 over 13 is the same thing as 12/13 over 1. You could see it either way. So could I consider it this way? Yeah, I sure could. But if I do that, remember, we're about to do Pythagorean theorem to find x. If I do that, then I'm going to deal with a fraction for my y, and that's not very nice. Okay, well, what if I consider this to be not 12/13 on a unit circle, but a height of 12 and a radius of 13? Because similar shapes maintain angles, sine of that angle does not change. Whether I consider this 12/13 over 1 or just 12 over 13, you get 12/13 for sine of whatever that angle is. And due to the similar shape, that's never going to change for that same ratio amongst your sides. Now, is it nicer? Yeah, it is, because finding this is a little bit easier than finding this. Because you're dealing with whole numbers and not fractions, it's honestly not a huge deal, but this would be nicer to find. Well, could you find x? Sure. If we understand that because you can inscribe this right triangle on a circle with this particular radius, we can always use the Pythagorean theorem. You can even think of just like a right triangle. Use the Pythagorean theorem or the equation of a circle and find out what your missing variable is. If you have 2 of them, you should be able to find the third one. So let's do it. Why we're doing this again is because if I'm required to find cosine, tangent, secant, and cotangent, this only gives you a y and an r. Well, because we now understand that this can be built on a right triangle, either on a unit circle or not, doesn't really matter, they're similar, then we can use that to find the missing variable like x, and then find cosine very nicely. And so we can do that. Now, this is the part that's very important. I really need you to not blow by this. Slow down the video and really pay attention. Not to like quarter speed or something, but really pay attention. Do you remember that when you take a square root on your paper, it is never okay to just put x equals 5 here. Why? Because when you take a square root, well, those power 2s, they do not maintain sign. You plug in a negative, you get a positive, you plug in a positive, you get a positive. So due to that fact, when we take a square root, we have to put a plus and minus in front of it. Now that appears to give us 2 different x's. Why does that happen? Here's why. Man, I hope you get this. If you get this, it's going to make sense for a really long time of what we're talking about. Why does that happen? Because imagine if I had not had my right triangle oriented this way, but had it oriented this way. Instead of a positive x, I'd have a negative x. Let's draw it. This would still be 13, still a positive radius. This would still be 12, still a positive y, but this would be a negative x. So what's the problem? The problem is there's some missing information here, and I hope that you're seeing it. On a circle, On a circle, you can have a radius and a y value that are the same and have two different x values. In fact, we talked about that in the last example a little bit about what if your y value is 12/13, like we have here. That's right here. That is going to have a point here with a y value of 12/13 and a point here with a y value of 12/13, but two different x values. Which one do you use? That's why it's necessary to have one of two things. You either need two trig functions, with any two trig functions besides like a reciprocal, like a pair like sine and cosecant. With any two trig functions, you can tell what quadrant you're in if you know the signs of those trig functions. So we either need two trig functions. We don't have that. We have just sine. We were able to find out x. That's fantastic by using some Pythagorean theorem or equation of a circle. That's great. But without two trig functions, or knowing the quadrant in which this angle resides, you can't choose the right one. You'd have two answers here, and that's not really okay for us. So I hope that you're understanding why we either need two trig functions to determine the quadrant, or we need to say something like, hey, sine of theta is 12/13. Okay, great. But your angle is in quadrant 2. Now, what's that do? What that does is answers the question on what sign should you pick. So one more time all the way through here as far as why we need two trig functions or know a quadrant. This is fantastic. This sine theta says that, hey, if that's positive, you're either in, man, get this, if sine theta is positive, you're either in quadrant 1 or in quadrant 2. That's great. However, x is positive for this quadrant and negative for this quadrant, which means cosine is positive for this quadrant, negative for this quadrant, because cosine theta is your x coordinate on your circles, whatever it is. So which one do you pick? Well, if sine's positive and we're in quadrant 2, that says that I'm going to have to pick the x value that is, well, let's think about it. X's are negative here. If I'm in quadrant 2, I'm going to pick my negative x. So which one do I pick? Well, cosine's negative, x is negative in quadrant 2, I have to pick the negative. I hope I've explained that well enough. I hope that you see that by understanding what quadrant you're in, you are determining your y value, you're determining the sign of your y and also the sign of your x. If we're in quadrant 2, our y is positive here. We already knew that. Sine theta is y, but our x is negative. Now we understand which one to pick. So we've used Pythagorean theorem, we got down to here, and we go, okay, if I am in quadrant 2, my x has to be negative. And now we're ready to find the rest of our trig functions. So we have a y, we have an x, we have an r, and after this is pretty easy to do. So let's go fairly quickly through it. Remember that we know that we're going to treat y as 12 and r as 13. Why we are doing that is so that we can easily find out what our x is and not have it as a fraction. You could have done this with fractions, that would have been okay to do. But this is a little bit nicer, and it doesn't matter because similar triangles maintain angles. Corresponding angles are congruent for similar shapes, and therefore sine, cosine, and tangent, they can't change. They're just a relationship amongst your sides. It's one ratio, whether the ratio is small, well, 12/13 over 1 or 12 over 13, it doesn't matter. It cannot change. And so I have explained it to you very well. So now we're going to go through and say, let's just assume that our y is actually 12 and our radius is 13. Can you find cosecant theta from that? Well, cosecant theta is the reciprocal of sine theta. So I can look right back over here and think, okay, if sine's 12/13, cosecant theta is 13/12. And that actually is right here too, 13 over 12. Cosine theta. Well, this is why we had to have quadrant 2, so we could pick the correct x. But now that we have that, we know that cosine theta is x over r, adjacent over hypotenuse, or the x coordinate over the radius. Any circle, this has a radius of 13. So that would be -5 over 13. Okay, pause right there and let this sink in. Notice how cosine theta being negative when sine is positive does in fact put us in quadrant 2. Also notice this. Even though we use this as having a radius of 13, could you think of this as negative 5/13 as an x value? Negative 5/13, that's less than halfway. That's like right here. That's like that point has an x value of somewhere in here, has an x value of negative 5/13. If you were to consider it on a unit circle, you're just dividing by 13 and shrinking that triangle back down to a unit circle from a radius of 13 to a radius of 1. This is a negative x value. This point here would have a negative x value and a positive y value. That's what we're saying here. Whether it's on a really big circle or a unit circle, it doesn't matter as far as what the cosine of that angle is. The angles don't change. How about secant? Because we have a reciprocal here, we can think of this as negative 13/5. Tangent's really nice. Now, you could certainly take sine divided by cosine and get negative 12/5, or you could think of this as y over x and just think, hey, here's my y, that's 12, here's my x, that's negative 5, that's negative 12/5, that's y over x. Do you see, though, that you could do 12/13 over negative 5/13? Multiply by the reciprocal there, and you get negative 12/5 also. Now that we've done that, cotangent, we can reciprocate tangent and get negative 5/12. Here's what I'm really hoping happened in this last example. I'm hoping that I'm making connections for you. I've seen far too many students treat these like formulas, and they never get it. It never really clicks that there's interplay here. That I don't care whether you're on a unit circle or a really big triangle or a really big circle. It doesn't matter, because what these trig functions do is take an angle and relate it to a pair of sides. A pair of sides is a fraction. Whether that fraction grows or shrinks, like both numerator and denominator grow at the same proportion or shrink at the same proportion, the ratio itself will not change. So it doesn't really super matter how you consider it. We think of it both ways, which is very cool for later on. Now, we are used to a unit circle, and that's fantastic, but I hope that I made it make sense that we're really just growing or shrinking a triangle to fit a radius that we want. And we can consider it two different ways, but it does work on a unit circle, and I've shown you that as well. I also hope that you understand the necessity to understand a trig function and another one, or a trig function and a quadrant, to determine the sign of how you use the Pythagorean theorem, whether you take a positive or negative after determining what quadrant you are in, whether x is positive or negative, and therefore cosine and secant are positive or negative, whether y is positive or negative, and therefore sine and cosecant are positive or negative. And then tangent and cotangent play along with those two things, because we have a positive or a positive, negative or a negative, or a positive or a negative, negative or a positive for quadrants 2 and 4 respectively. So I hope it makes sense. It's not all that hard. I'm going to put one more up on the board that we're going to work through, and then we're going to call it good. Let's go through one more example. Let's say that you know that secant theta is 2, and you're trying to find out the rest of our trig functions. Can you do it without this? No, you really can't, but not because you can't find out x and r with this, we're going to see that in just a second, but because you wouldn't be able to figure out the sign of y, positive or negative. And not being able to do that, you wouldn't be able to figure out sine or cosecant, tangent or cotangent. And so we really need to know on what quadrant this angle is. That's the reason why they're giving you this. So let's go ahead and figure that out. Let's think about where secant is positive. Secant matches up with cosine. And so we're going to look at the quadrants in which cosine is positive, because that creates secant positive for us. So cosine is positive here, not here, not here. Because why? Why is cosine and therefore secant negative here? Because cosine is the x-coordinate on a unit circle, or the adjacent side of a triangle here. And that would be negative for both of these quadrants. That's why cosine is negative here, is because the x is negative. Look, here's our x-axis. It's all negative for every point on this unit circle. All the x's here would be negative. Therefore, all the secant thetas on these two quadrants are also negative. Well, secant is positive where cosine is positive, or x is positive. That's in quadrants 1 and 4, so it matches up with cosine. So I know that if I'm not given this information, that I am in quadrant 1 or 4. I need you thinking of that like every time. Think, what quadrant am I in for my angle? So quadrant 1 or 4 here, I need more information. I need what the y is doing. So I'm going to have to get like tangent or cotangent or cosecant or sine. I'm going to have one of those things, something with a y in it, to determine whether my y is positive, that's up here, or negative, that's down here. And that would determine my quadrant, either 1 or 4. And so we're going to look at this and say, hey, sine's negative. So where is cosine positive and sine negative? Cosine's positive where x is positive. Sine is negative. That's what this means. Sine theta is less than... Got too excited about my thetas. Sine theta is less than 0 or negative where y is negative. So if secant is positive, therefore cosine is positive, you're in these quadrants, your x is positive. And if sine theta is negative, that means your y is negative. Sine theta is y. That means your y is, that's this quadrant. X is positive, y is negative. That's how you figure it out. We can go and just look at our signs, but I'd rather you understand what's going on. I mean, that's how I always teach you, right? Is to make sure that you really get what is going on here. Don't just use the formulas. Really walk your brain through that. It'll help you out so much when we get to graphing, when we get to calculus as well. So I know that what this means is cosine positive, sine negative, quadrant 4. Now that determines something for us. That says that sine and cosecant should be negative, secant and cosine should be positive, tangent and cotangent should be negative. So let's figure it out. If we know that secant theta is 2, let's treat this like a fraction. I know that this could be something on a unit circle. It would be 1/2 for x value, because this is 1 over x. So let's think about it that way. If secant theta is 1 over x or r over x, r being the radius, if I extend this on a similar shape. So this would be r over x, which means that our x would be 1. So secant theta is r over x. Secant theta would have an x of 1 and r of 2. Now, we can easily figure out cosine theta from this naturally because this is just a reciprocal. So I could get 1/2, no problem. You do not need to do any of this if you were just looking for cosine theta. You'd be done. But if we are looking for the rest of the 4 trig functions here, sine theta and the rest of them, well, then we need to know the y value. I have an x right there. I have an r right there. Could we use Pythagorean theorem to find the y? Of course. So the Pythagorean theorem or the equation of a circle, same in this case. We can write that out and then solve for whatever variable we're missing. A trig function should give you 2 of them if you have this fraction for whatever angle you're given. So let's go ahead and subtract. We're going to get ultimately, here's 4 and 1, y squared equals 3. Let's take the square root of that. If we take the square root, you have to show the plus and minus. That tells you you have 2 possible outputs, and then this is going to tell you which one to pick. So y equals positive or negative square root of 3. Because we said that sine is less than 0, sine is negative. Sine is the y here, so we have to pick the negative. And this lets us find everything else. So we can go through and figure out sine theta and then cosecant theta, tangent and cotangent theta. So sine theta. Sine theta is going to take your y divided by your r. That's how it always works. That's opposite over hypotenuse, or the y coordinate over your radius on some sort of a circle. This is not necessarily thought of as a unit circle. You can. Negative square root 3 over 2. Quadrant 4, sine with an x of 1/2, negative square root 3 over 2. Cosecant reciprocates that. And after rationalizing, we get negative 2 root 3 over 3. Tangent compares your y and your x. If you have an x and a y, Don't be going and taking sine divided by cosine. You'd have to simplify that complex fraction. Let's just think about it as, hey, tangent's y over x. Here's your y. You know that it's negative and not positive because of the quadrant. That determines that tangent is also negative because of that quadrant. Quadrant 4, tangent's negative, and you see that. Sine's positive, sine's negative, cosine's positive. Negative over positive is negative. That'd be negative square root of 3 over an x of 1. Y over x. Cotangent reciprocates. And after rationalizing, we get negative square root of 3 over 3. I hope I've made it make sense. Man, I really hope that I'm making some connections for you that if you've done trigonometry before, that maybe you haven't ever seen. If you have seen them, maybe you haven't ever understood. I hope that you understand them now. If this is your first time through, I promise you that understanding what I've talked about in this video will help you extremely when we get to right triangle trigonometry, past that, and when you get to calculus. Because sometimes we miss the connection between a unit circle and the sine and cosine, and right triangle trigonometry, the sine and cosine, all the trig functions, they're the same. We're just making the triangle bigger. And we can do that because angles do not change on similar shapes. That's why it works. So I hope it's making sense. I hope I'm building connections. I really need at a minimum for you to understand that cosecant and sine match up a little bit. They're reciprocals. Secant and cosine match up. And if you get that, and cotangent, tangent match up, that you will have these reciprocal identities down. We won't have to always go back to formulas. So we're going to come back. We're going to talk about whether sine and cosine are even or odd, and the Pythagorean identities. So we're going to take this and we're going to run with it a little bit. So I'll see you for that video.